Hello, hi everyone. Welcome to the another video. We are going to look into one of the very famous algorithms that we have in all of data science and machine learning. The algorithm that I'm talking about today is gradient descent algorithm. It's like one of the most important algorithm, and having a high level understanding of it is like really a must if you want to understand like the back-end calculations or the back-end optimization that happen across machine learning, right? It's one of the backbone of deep learning algorithms or deep learning as a whole, and it has tremendous implementations across all the other algorithms as well, right? Cool. So to start with, I think the first thing I would like to define over here is the problem statement. We would try to look at what problem we usually face and then where does this algorithm come into place, right? Cool. So again, taking example of the normal linear regression that we typically have, what we typically do is we make a prediction over here, which is y predict, and we estimate, we are trying to create a linear line over here, which will be of the form y equals to mx plus c. And using linear regression, we basically estimate the values of m and c, which gives us a y prediction, right? So if I were to plot it on a scatter, say this is the actual data points that we have. Using linear regression, we try to plot a line, right? We try to come up with an equation so that we can quantify the relationship between our x and our y variable here. Correct. So how do we know that this is the best line, or how do we know that this is the line that defines the distribution in the best possible way, right? So which line is the optimal line here? That is the question that I'm asking. So how do we find this optimal line or the best line for our regression? The thing is, somebody can draw a line here and argue that is a better line. Somebody could draw a line here and argue that this line is better than the others. So how do we measure that? I think a simple way of doing that is whatever line that you have, we try to see basically the amount of error that we have in the prediction, right? For example, this is the actual point, right? At this point, the prediction is this, correct? This is what our linear line or our prediction is predicting. So for any given line, whatever line you draw, you can try to check the errors associated with that given line, which is nothing but the y actual minus the prediction that you have. Your prediction is this mx plus c, like whatever coefficients that you came up with for the line. This is the error, y actual minus your prediction. So this error will be associated with each and every point in the data. So what we typically do is we take a sigma over here or summation of this. Again, one another way of how we typically report it in a linear regression is you take the square of it. Again, the understanding here is that few points could be over predicted, few points could be like underfitted or below the line in a way. So we could have those positive and negative, but we are not interested in where the points are. We are just interested in the magnitude of the points, right? So that is why we take the square of it. And this is the function that we're trying to minimize here. So for a line for which this equation is minimum, right, for which the error is minimum, is going to be my best fit line. So that is something that we are trying to find here. Cool. So like this is something that we have to minimize. And now in the code, I think what we'll look here is we'll look at some random guesses that I make here. Like how do we find this, or what could be the way of solving this equation, like minimizing the error function that I have here. Cool. So I'll switch back to the code. I think the first thing that we are doing over here is again generating some synthetic, right? Generating some synthetic data. And again, I have come up with some random equation of the line that I'm looking for. So it's like y equals to mx plus c plus some random noise that I've added in the data. I've created a random prediction function, sorry, a prediction function that is y equals to mx plus c. Similarly, I've created the error as well. That is y prediction minus y true, a square basically. We're taking the square of that function. And I've also added mean. So we basically across all the data points, we take it and take the average of the error. So that is how what we are trying to minimize here, the loss function. Cool. So if I run it, I think we'll be able to see the kind of data that we are coming up, right? So this is the synthetic data that we have come up. We have our X variables, we have our Y, we've added some random noise. So we do see some points that are straying away from exactly the center or the state distribution that we would expect here. Cool. So our data is set. The next thing is again, let me write the equation at the top so that we can always aim. I'll write it here. So what we're trying to minimize over here is the error, right? I'll write it denoted by E, which is in a way can be represented as Y actual minus Y prediction. Taking the square of it, summing it across points, and then taking the average. I equals to 1 to n. N would be the number of points that I have, right? This is something that we are trying to minimize. Now again, it seems like a very mathematical problem, and that is true as well. So the first thing that anybody could try to do is we can pick some random points and then see like if I'm able to get a sense of it, right? Let me pick some random values of say M and C and then see if we are able to come up with some sense of it, like how should we proceed or not. So let's try to solve this so that we all can develop our understanding here as we move ahead, right? Cool. So for those random guesses, what I have done over here is again, these libraries, what I've done over here are for visualization, NumPy, so on and so forth, the basic libraries. So this is the function that I've come up with, which is doing nothing but generating some random guesses. So what I take is I take my X variable, Y variable, some initial values of W and B and steps. So I'm taking three guesses in a way here so that all of us could see like if I proceed with guesses, what dilemma or what kind of problem we are stuck with, right? So we make our guess variables, we initialize our W and B, and for the number of guesses, we compute the current loss using the loss function that we created above, right? Now for every guess, whatever guess, I'm taking three guesses, I'm trying to tweak the guess values of W and B 10 times because I'm running the loop 10 times so that I could minimize this loss. So in a way, what I'm doing is I'm taking three guesses here. It's taking three guesses here. And for every guess, I'm trying 10 times with random values again to basically minimize the error that I get here. So you can see this is like a brute force algorithm that I'm trying to come up with here, right? So I am taking three number of guesses. These are my number of guesses. And for each guess, I try to optimize the guess by trying 10 different things. Again, as you can see here, this is quite random, quite brute force way of doing things, right? But that is the first thing that anybody would try to do when they would try to solve this problem for the very first time, right? We don't know what gradient descent is, so what we can do is we can try to see how the data behaves when we do this, correct? So I go to the eraser, let me erase these things. Perfect. This is the feedback function we create, and then I think we can ignore the plot functions that I've created here. What I'm doing in the plot function is basically plotting my prediction on the actual loss plot that I'm going to get here. Right. Now, again, one thing that I want to touch over here is as I have multiple variables, right? We have two variables here, and loss is a function of both of them, right? So I'm not going to get a 2D plot because what happens in 2D plot is we have one variable and the y side is basically the function of that, right? It's like f of x. But now in the linear regression, as we typically see, for the example that we are seeing, we have two variables, m and c. M being the slope, c being the intercept, right? So the function that we're going to get is a 3D function, and that is why I have written down this code so that we can visualize how it's happening. So at a high level, let's see what happens if we try to go about it using the brute force algorithm. All right, let's Let's go back to mouse, and I think that's it. Initializing with some random values, and just let me run it. Great. So, all right, I missed it here. Yes. So again, as you can see, is we are getting a 3D plot here where we have our weight and where we have our bias, the two things that we're talking about, slope and the intercept in a way. And this is the loss associated with them, right? So as you can see, we are getting over here a 3D plot, and you see three dots over here which are quite close together, right? But the thing is, the task that we're trying to solve for here is this is my error function, right? How it's dependent on both weight and my bias. What I need to do is to solve for this equations or values of B and W, I need to get to the minimum point here, right? And as you can see, the guesses that I have done are quite random. They're not helping it out. But the purpose of showing you this graph over here is so that you can visualize in the 3D space how the error plot or error graph would look like, right? So as you can see, the random guesses are kind of fine, but it would take like so much amount of resources. And if I just keep on doing this random hit and trial error, and that is why where gradient descent comes into play and solves for us. But I wanted to just show you guys this graph so that you can visualize the error surface, right? And again, now building our own logic towards the solution or building our own understanding of gradient descent to solve for no matter where I start with, right? For example, if you're starting from a point here, I need to understand now, uh, I need to understand like in which direction I should move next, right? So again, there are two directions associated. One direction is towards the weight, and the other direction is towards the bias, and the other direction is towards the waist, towards the weight, right? So I need to find basically which is the optimal direction to move at. So it's going to be somewhere in the middle of it, right? Because it's dependent on both of them. So this is the thing that I need to figure out, like which direction we should move in whenever we are at a random starting point, right? So that is where the intuition comes into play. It's known as gradient descent because at any point, for example, if you imagine you're in a valley, what you can do is you can close your eyes and understand and feel the slope, right? Whether it's ascending or descending. So if you're standing here closing your eyes, if you try to move backwards, you would notice, right, that there's an increase in incline and you are having to climb up. So that is what you won't want to do in this algorithm. And the intuition is quite straightforward. We try to go towards the steepest descent over here. So that is like a high level understanding of the algorithm that I wanted to give you. The basic intuition is quite similar. We get to a point here, then we again check which direction is the best, has the nicest slope downwards, and we do this, we do this, we do this, and we then, yeah, we get to the actual minima. And whatever values of W and B are associated here are going to be my final answers for this algorithm. For any algorithm, again, the loss function could vary here, guys. Again, the curvature or everything that you see over here might change, but the understanding, the basic understanding is going to stay the same over here, that we're trying to get to the minima, and we are trying to go towards, we are trying to basically descend downwards from this curvature that we have here, right? Cool, I'll erase these things. I'm not erasing the above error function so that we all can see it. All right, so yep, let me close this. So what we did create some random data, we did some random guesses, and what we see is we are not getting to the minima error. We are not able to minimize this using that way. And I think we have another plot here that I kept. I think this was just to show you what actually is happening. So this is our actual data, and these are my different guesses. So you see, like we're still quite far away from explaining the true behavior, right? The actual line should be somewhere passing through the data. So the error is still quite high. Cool. So now I've created a function here. Before talking about the function, I'll talk about the gradient descent algorithm in a nutshell. And we'll talk with I'll explain to you guys this with the help of a 2D plot. I think that would be much more easier. So for example, we had only one variable or only one variable in our equation. Say we only had x, right? And we had a function of x, and I'll assume the functional form to be similar. So if I'll assume it to be of the form x square itself. So say this is our error, right? The y-axis is my error here. Now, let's say if you start with a random point, right? This is the random starting point that you have. The first thing that you would want to check over here is what's the slope here? What's the slope looking like at this point, especially of the error function, right? So the slope is looking downwards, right? So if the slope is looking downwards or is negative in a way, then what you would do? You would want to move in that direction, correct? So your next update would move in the direction of slope. So how you can remember is the new x that you're going to get, you are going to make some changes in the old minus the slope that you get. That will tell you the direction you should change or move. This is very important thing, guys. I would want you to take some time here and try to understand why that is happening. So you start from here, you check the slope. Slope is negative. So you get some random negative number here for slope, right? So for example, it's negative 4, any random number. So your new x is going to be in this direction. It's asking you to move here. So you have to add something to the old. So that is why negative negative becomes positive 4 and you increase or move ahead here 4 units. So you're moving towards the minima here, right? So you will might jump to here and then you might jump to here, so on and so forth. Cool. So that is like the basic intuition that the new point is going to be determined based on the old point and the slope that you have. But there are few things that we need to account for, and those two things are also quite important. I think we need to talk about them as well. I'll just rewrite the equation on the right so that we can see it, and then we'll talk about that, right? So, yes, let me remove these random points here. That is the starting point. Perfect. So the equation that we're trying to solve for is x new is equals to x old minus slope. So that is the generic idea that we get, right? Cool. So in some cases, now what might happen is the value of slope could be such that the jump that you're taking here, it could be really high, right? If the slope is minus 40, it's not going to be scaled properly or whatever. So you might overshoot the minimum. And then when you're here, it will ask you to move in this direction. You might reach here. The slope is so high that it's never going to converge. You're always going to jump ahead, so on and so forth. So there's this problem with only using the slope. And that is where we introduce a term that is learning rate. LR. Got it? So what learning rate tries to do is it's basically a scalar thing that we do and we multiply it with slope to account for the amount of jump that we are taking here. We don't want the jump to be very big. We don't want it to be very small, but we try to take some optimal learning rate depending on the data that we have, but it controls for this factor, right? So that we can take small jumps so that we can get very close to the minima here. So that is the understanding. And the equation simply changes to, I'll just write it x dash x minus, this is how we typically denote learning rate times the slope. So this is the most important equation. And this is how we keep on moving or improving our predictions here. So this was for one variable. We'll also talk about how we are going to solve for m and c when we have two variables here. But I hope the idea makes sense here, right? Now, before moving ahead with what happens when we talk about two variables, there is also another thing that we need to focus here, like when does the algorithm stops, right? So when do you stop? So you can keep improving your X following this approach. If right, you can keep moving here. You might get very close to it, right? But the slope value will be so small that you might never actually get to the true minima. So that like the absolute true minima, but from a machine learning or algorithm point of view, you are actually at the minimum only at those points. So the one thing that we can check over here is if the improvement that we are making x dash minus x is very, very less, right? Is less than 0.000001. So in a way, it's showing or telling you that the model has saturated and you are actually at the minimum. And secondly is number of times you're going to run this iteration, right? How many times are you going to update this? So that is going to be number of epochs that we have. So again, it's to keep a very important thing in our mind that we are always resource restricted, right? We cannot run a loop forever and then expect to get a good result. So those things cannot be there. So that is why we have to keep these two ending conditions in our mind. Cool. So I hope these things made sense in a 1D dimension. Now I'm going to write the equation. I'm going to solve for the equation that we have above. Let me just get rid of all of this. All right. I don't want to delete it because it will delete the equation above as well. Cool. So basically, what this equation turns out to be, right? It's going to turn out to something like this. It's going to turn out to sigma y minus mx minus c square. Now, y and x are going to be actual data points in the model that we are going to get, right? So this is also going to be a scalar, so ignoring this for now. So how do we solve for this, right? So the first thing that we need, as we just saw, right, we need to understand the slope. Now slope here is a function of m and c. So what we need to do is we need to understand what's the slope when I look towards m. So what I'll do is I basically differentiate the error function with respect to m. So I'll differentiate the equation there that we have, right? Now basically if m is considered as a variable, correct? So how is the equation going to look like? It's kind of the form of x square, so it's going to be 2x, and then we different into the differentiation of other. So this is constant, this is 0, this is going to be minus x, and that is again a constant, so that's going to be 0, right? This is what tells me the slope when I look towards the direction of m. So imagine you're standing somewhere in that 3D curvature plot that we had, right? And you look towards one direction, and this is the slope that you're getting there. And the only other direction that you can look right is the c. So what you do over here, you differentiate with respect to c. So when you differentiate with respect to c, again, this is going to be the variable, and what you can do is you can just differentiate it. It's going to be x square again, so 2 mx minus c, and you differentiate with respect to c. This is constant, this is going to be 0, this is again m is constant, x is constant, it's going to be minus 1. So this is going to be how you basically determine the two slopes. And once you have the two slopes, team, uh, then is what you can determine what the next step should look like in the direction of M, and the next step should look like in the direction of C. So you have these two slopes, correct? So new X, or basically this is M, so new M is going to look like minus old M minus the learning rate that you take and the slope, right? So this equation would solve for slope, give you the slope there. If you put in the values where you are currently, and similarly you can get the values for C. The new C dash has to be C minus learning rate times slope. This is going to give you two new values of M and C, and you're going to try the function, create another line at these new values, and see if the error minimizes. This is going to be the best way to move forward if you want to minimize the errors. And again, as you know, when do we stop? When the prediction does not improve by a lot, does not improve a lot, or we run out of epochs, right? This is the algorithm which can be used to solve multiple or different kind of error functions that are there, right? So I'll quickly erase all of this. Again, I know we talked about a lot of things, but I hope the generic idea is with you guys, right? So the new point that we're going to make or new step that we're going to make, we make a new step by looking at the slope that the slope associated, right? So that is the basic idea of this algorithm. And now I think we can look at the function that I created. So this is the gradient descent function. We take x and y. We have our initializers where we can start from any random point. We have the learning rate, how you want to improve, and the epochs. Right. Now for we run this algorithm as many times as we have epochs. So that is like the threshold of the number of iterations that I'm going to run. We'd make a prediction, we compute the loss, we compute the gradients. So this is again the gradient functions that are being calculated here. This is kind of similar to what I just did in mathematical form. We update the parameters. So weight is equals to weight minus learning rate times the slope that we have. B is calculated in a similar way. And I'm storing them here so that we can visualize it, right? Finally, I'm calling it, I'm giving these parameters and let us see what happens. I think the first plot over here is for the errors. And yeah, you can see how the error minimizes, right? So epochs is the number of iterations that you have run, and on the Y we have our error associated. And you can see the error keeps on dropping here. That is why we converge and the error is almost stagnating at this point. So this is how this algorithm is working in a magical way, right? It's moving in the direction of the descent in a way to minimize the errors, and that is how we are able to solve for this. But this is like one of the very, very important algorithms that we have here. Cool. I think the next thing that we're looking for here is again another animation that I've added here. So I can quickly run this point so that we can look at how it's actually happening, right? So this is again a dynamic chart, and you can see when the epochs are increasing over here, the loss is slowly, slowly decreasing. We are updating the parameters of W and B to basically find the best line that we can. What you notice over here, we stopped at 50 pokes. We could have improved the line here a bit further, but just for visualization purposes, I hope that made sense, right? So this is how it slowly improves, trying to understand which is the best direction to move in. Cool. So I think this is like a high level understanding of the algorithm that we have here. The next parameter that I would want to touch base over here is especially the learning rate that we have, right? So for example, what we see over here based on the learning rate that we have, I want you to focus on how the error is being minimized here, right? So the only question or only debate that we might have in our minds is what happens if the learning rate is too high. So let's update the input learning rate parameter to 1 and then let's run point 1 and then let's see. So when we improve the learning rate, you see the error is being minimized quite early on and don't need as many epochs, right? You have reached the best line around, I would say, 5 epochs in a way, or 5 iterations, and we are there, right? We are almost there. The, so somebody might say, let's keep on improving the learning rate. Let's improve the learning rate to 10, and then let's see what happens. But that does not work here, right? So what has happened now is our learning rate is so big that we're jumping ahead, right? We're not getting, if I talk about this, a learning rate, we start from our learning rate is so high. The jump that we are making, we are overshooting. We are getting somewhere here, and then we are getting somewhere here. So the error is still too high. We are not making any progress here. So having too high learning rate is not good. Learning rate should not be very high. This is something that we need to keep in our minds, right? This is what I wanted to visualize. So whatever data that we had, we have to play around different learning rates to see how the error is being minimized here. And I think that is one important key takeaway that I would like to add here. But yeah, I think this is it. Just to summarize, I think gradient descent algorithm is one of the most powerful algorithms that we have in data science and machine learning. The basic idea is we move towards minima by identifying the slope of the error function, like which moving in which direction would basically minimize the error function. So it basically boils down to a simple equation that is whatever new thing that you're coming up with, it looks at the old minus some learning rate and slope. The rest parameters are epochs, how many times you want to run the tries, so on and so forth. So yeah, I think that is a high level idea of it, and that is what I wanted to cover in today's session. Cool then. Thank you, everyone.